All right, guys, so I posted a worksheet with 2 problems on it. This is what I have written in red. Don't bother copying. You could just print out that worksheet and just follow along. This really just picks up from the lesson that the AP board put out that I attached to my link. I highly suggest you looking at that lesson. It seems a little basic in the beginning, but really the reason why it's so basic is so that you understand questions like this. So we're going to move on and just see how we model situations using differential equations and what comes to it from it. So the first example was labeled exponential growth model. So in this question, they're saying the rate of change of y is proportional to y. So we saw that in our lesson that when we saw a rate of change, we said it's the rate of change of y. So we're going to see a dy. Now they're not telling us with respect to a certain variable. This is inferred as it was in the video with time. So this would be dy dt. Okay, because it's exponential growth that changes with time. So the rate of change of y, that's shown by dy dt, is proportional. So when we saw proportional, we saw it as a constant to y. And then they gave us some information here that when t is equal to 0, y is equal to 2. That is an initial condition. My highlighter just ran out. Oh, there it is, got the wrong side. So this is considered an initial condition that we're going to use, as well as t equals 2 and when y is equal to 4. So we're going to use that to solve for our constant and different variables along the way. So remember, when we have a differential equation and we want to solve for it, we need to integrate. So the first step of integrating is we want to separate these variables, because right now we know we can't integrate in this form. From day one lesson, those variables have to be separated. So you always start with the dy and the dt's and get them separated. So I'm going to multiply this side by dt and this side by dt. This crosses out, and on this side I'm left with dy is equal to ky dt. So this is telling me that only the variables with t can be on the right hand side, and only the variables with y can be on the left hand side. So I'm seeing that this y needs to move. So I multiply this side by 1 over y, and I do the same on the other side. That cancels that out, and I'm left with the constant dt is equal to the integral of 1 over y is the same thing as y to the negative 1 dy. All right, now I'm safe to integrate. So those signs can go on, and I can begin to integrate. When I see y to the negative 1, we know that is an ln situation. I always want to use u sub if the base is bigger than a monomial, and it's not, so I can just go into changing this to the ln of the absolute value of y. The dy turns into plus c is equal to, now this is a constant. So when I integrate it, adding the 1 to the variable of integration is t, so this becomes kt, and then plus c. So again, we're trying to solve for for y. So let's move that c over. And remember, that does not cancel the c out. It just creates a different c. So we're just going to leave it like so. And I want to get to y, but it's part of ln. So this is that we've already seen this in my other video, that we need to change it to exponential form to get the y out of the absolute value, or out of the Lagrange. So this turns into the base e raised to the exponent. So the absolute value of y is equal to e, and then this is raised to the kt plus c. And in my other video, you also saw that whenever you see an addition in an exponent, that means that the bases were multiplied together. So I can rewrite this as kt times e to the c. Now that's important, because e to the c, we also spoke about this in my other video, that e to the c is just another constant. So I'm going to change that to equals, this turns into c, and we got e k to the t and the absolute value of y. So we're here. I'm at the point where I can start to solve for my variables. My variables here that I want to change, because time is our independent variable and y is our dependent, so that's going to stay, but c and k we need to solve for. So I'm going to first start with this initial condition of t equals 0 when y equals 2. And I'm just going to plug that into the absolute value of 2 instead of the absolute value of y is equal to c e k t. The absolute value of 2 is equal to c e k times 0. And then this would just become e to the 0 power, which we know that e to the 0 is 1, so my constant is just 2. So I just solved for the constant. So my next step is to go back to my problem where it's the absolute value is equal to 2, e k t. So I plugged in the 2 that we solved for. Now I used this condition already. If you see, that top condition was used, so now I'm going to use this bottom condition, and I'm going to get that the absolute value of 4 is equal to 2 e k times 2. So this just becomes 4 is equal to 2 e to the 2k. I divide by 2, I divide by 2, e to the 2k is equal to 2. And now to get that k value down, I have to apply log. So I'm just going to ln both sides, and that 2k comes down, and I'm left with ln of 2 is equal to 2k. And we know that ln of e just turns into 1, so that goes away. And last but not least, we divide this by 2. So now that I know k is equal to 1/2 ln of 2. So I just solved for the equation, the particular solution, y is equal to 2e to the 1/2 ln 2t. Now, the one thing that I wanted, so this is your answer, but the one thing that I wanted to bring your attention to is this is an exponential growth. And this equation here looks a lot like an equation that we studied in Algebra 2 when we saw continuous change occurring. So if we see this, y equals c e k to the t, I'm wondering how many, and it's not the easiest to see right by yourself, but how many now see that this mimics a equals p e r to the t. And now if you can recognize that, that's going to make your life a lot easier in a future problem. We'll do the next one, where you'll see that if it's modeling some sort of growth, some sort of exponential increased growth, we're going to see that it will follow, that c is your principal, it's your initial amount, and that k is your rate of the continuous change. So just keep that in mind, because that is a big piece to help us. All right, so we're going to continue on to example number 2, which is typed up for you, but I just wrote it out. So here it's population growth. So I'm reading this. Suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment, and then there was 300 flies after the fourth day. Approximately how many flies were in the original population? Well, as I read this, I see that this is an exponential growth. Just like I said before, I said, oh, that reminds me of APRT. But in this problem, and what we're used to, it's y equals c e k t. So if I didn't recognize that, I would have to go through all the steps that we did in this problem to come to this form, to then start using our initial conditions to find our missing variables. So if you miss it, you would just have to do this work. So it's really important to try to decide, does this follow that exponential growth model as I saw before? So since I see that it does, it's exponential growth is mentioned, it's talking about increasing, I'm comfortable to say that this is the equation that I can use. So here I go ahead and I write down my conditions. There were 100 flies on the second day. So that initial condition is when your input, your time is 2, your the amount that was outputted was 100. And then on the 4th day there was 300 flies. So now what I'm going to do is I'm going to put in those initial conditions and see what comes out of it. There was 100 flies when my time was 2. So all I can get to here is that CE to the 2K. So that's 1. Now I took care of that one. I'm going to use that one into the same equation. I'm going to say when there was 300 flies, my time was 4. So this is just 300 is equal to CE to the 4K. So now no variables went away. So I'm looking at this, I'm seeing that they both have a C, and that constant's the same for both of them. So I'm going to solve both equations for C. So I get that C is equal to 100 over 2K, e to the 2K, sorry. And this one, C is equal to 300 over e to the 4K. So I'm sure you're guessing already that you can just set them equal to each other, which is exactly what you have to do. And we're solving by just cross multiplication. And then I want to get my e's together. And here, if I have the same base, I can subtract those exponents. So it's e to the 2k is equal to 3. And now I ln both sides. And I get 2k is equal to the ln of 3. Divide by 2, divide by 2. So now I know that k is equal to 1/2 ln of 3. Now remember, I was looking for my constant. So once I know my k, I'm just going to pick one of them to plug into. I'm just going to plug into this one. I'm going to say C equals 100 over E2 and then 1/2 ln of 3, which is interesting because that crosses out. I get C is equal to 100 over E ln of 3. And again, that's that box. So C is equal to 100 over 3. Therefore, C is roughly 33 initial flies. Hopefully we followed that and I didn't run out of time.